So you'll get the idea of groups in the moment. Okay. So what a rotation group means? So we'll be taking rotations in 3 dimensions. First, let's consider rotations in 3 dimensions. Okay. And then you will get the idea of this group. Okay. So let's consider a rotation. Let's say an arbitrary rotation in 3 dimensions. Okay. So we consider a vector. Let's say. So you consider a vector R. Okay, so it is having the components x, y, z. Clear? So now let's do the rotation by some R. Okay, R is a rotation matrix. So you just rotate your coordinate system. Okay, clear? So what? Okay, so it means this R will act on this R. So you will get some R prime. Clear? So once you rotate, what will happen? So what does it mean? So it means you are having some x prime, y prime, z prime is equal to some R acting on this x, y, z. So we define rotation with respect to some object, how it acts on. Okay, we define rotation in a given plane. Clear? Okay, so it has to act on some object. Clear? And the object here is. And the object is vector itself. Clear? Okay, so think, suppose if you are in xy plane, let's say, so you rotate your coordinate system. So you go to x prime, y prime. Clear? Let's say through an angle. So what will happen to the vector? Let's say in the old coordinate system, the vector is defined as some vector b. Clear? So what will happen? Some vector is there, what will happen? So the components of the vector will change, is it? So how they change? So you can write the components of the vector in this fashion. Like this thing, a rotation matrix in 2 dimensions, in the xy plane, acting on dx. Clear? So you can think this vector as the position vector of some point. Clear? Okay, you rotate your coordinate system or you make a rotation, let's say, in xy plane, so you will get some new object, the new components of the vector. Clear? The same thing is here. So I am considering, let's say R is a rotation matrix. Okay, so R is you can think R defines an operation which rotates your vector. Clear? And you will get a new vector. Clear? So you start from an old coordinate system and you go to the new coordinate system with the help of this R. Okay, we need to figure out what are the properties of this R. I have not specified yet what R is it? So here if you see what is R, okay, so if you see this R is simply cosine of theta, sine of theta minus sine of theta, cosine of theta. Is it true? So that is Vx prime is equal to Vx cosine of theta plus Vy sine of theta and so on. So this R you know. So it is the rotation in xy plane about z axis. Clear? Got it? Okay. So now let's move a little bit further. Okay, so what this rotation is doing? So if I am making a rotation in, let's say, xy plane, the length of the vector remains unchanged. Clear? Is it true? Yes. So if I make the rotation, okay, let's say in 3 dimensions, what will happen to the length of the vector? So length of the vector is always an invariant quantity. Clear? So that's a number. Okay? So therefore I can write, let's say, this way, how I define the length of the vector. So if R is given by, let's say, I should have put it in the proper form. So this R is actually this column vector. Yes. So I should write this vector R as a column vector, x, y, z. Okay? Got it? So because this is a 3 by 3 matrix and it acts on this column vector, you get a column vector back. Okay, so the length of the vector is given by R transpose R. So let's calculate that. So it will be x, y, z, and x, y, z. How much is that? X square plus y square plus z square. So the length of the vector remains invariant. Okay, so this is the length. So therefore, okay, length of R remains invariant, okay, under R. Clear? So what does that mean? It means R prime transpose R prime, that is same as what? R transpose R. Is it? So this is the length of the vector in the primary coordinate system, and this is the length in unprimary coordinate system. Clear? So under rotation, this remains invariant. What it means? So I can write this R transpose as R. Okay, what is R prime? Tell me. R prime is R. Okay, it's transpose. What is this R prime? R. So that's equal to R transpose R. Clear? So let's write it. So it is simply R transpose R. R is equal to R transpose R. Okay, so this is true. Okay, so listen, what is unknown to us? R. Is it? So the solution for this very equation, okay, if the length has to be invariant, it means this R transpose, if I put this R transpose R equal to an identity matrix, because these are vectors, column vectors and a row vector. So if I put this as an identity matrix here, then you are having R transpose R same as R transpose R. Clear? So that means this equation satisfies if R transpose R is equal to identity. Clear? Okay, so now we have got the first property of this R, is it? So it satisfies this very condition. Clear? So what this condition is known as? So if you, let's say if you are having a matrix, if you take the transpose of that matrix, multiply it with itself, that means O transpose O is equal to identity. What are those matrices known as? Orthogonal matrices. Clear? So that means R is an orthogonal matrix. So this is the definition of orthogonality. So these are orthogonal. Clear? Got it? Okay. So I am considering, okay, so we can say this is a 3 by 3 orthogonal matrix. Clear? Okay. So now tell me, so if this is satisfied, so it means I can write this R transpose same as R inverse. Can I write it? Let's say R inverse exists. So you can multiply R inverse on from the right. So you can write R transpose is same as R inverse. Clear? So this is the another definition of the orthogonal matrix. Clear? Okay. So let's take the idea, okay, of the groups. Okay, look here. This R is a rotation. Clear? So let's take this simplest of the case, rotation in 2 dimensions. So it is cos of theta, sine of theta. Let me take, for example, let's take, okay, in 3 dimensions, cos of theta. Okay, is this the rotation in 3 dimensions? Huh? Everybody? Okay, so let me write. So it is the same thing. You are having x prime, y prime, z prime. When you rotate in 3 dimensions, what you get? This matrix multiplied by x, y, z. So the same thing, the diagram I earlier showed. Clear? So now tell me, what is the value of theta? I can rotate, let's say, in xz plane, how much? From 0 to 2 pi. Is it? So I can change theta continuously from 0 to 2 pi. Is it? So you can take infinitesimal amounts of theta. Clear? And add them up. So that means this angle is a continuous variable. So you can think this angle as a parameter corresponding to rotation in xy plane. Clear? So this theta is here what? A parameter specifying me the rotation in xy plane. Clear? And it's a continuous rotation. So that means, okay, how many elements of R I can have? Let's say in this way, how many elements I can have? So how many numbers are there from 0 to 2 pi? Infinite numbers. So that means you will be having how many elements? Let's take the set of R. Okay, let's take this set. Okay, so I will call this as R of theta. Let's take this set R of theta. Okay, and theta goes from where? Theta belongs to 0 to 2 pi. Clear? Okay, so how many elements are there? Infinite number of elements, is it? And these infinite number of elements, okay, so I can call this as a set, is it? So much ever? And one more kind of thing is that all these elements are connected by a continuous transformation, is it? So you can generate, let's say you have, let's say R of 0. You can go to R of some 0 plus delta theta, is it? Then you can go R of 0 plus delta theta plus delta theta till you reach to R of 2 pi. Clear? So that means you can get these elements continuously from a given element. So much ever? You got my point? Now if I am having such kind of structures, okay, so let's take the set of these elements. Okay, R. This R can be a rotation in XY plane, it can be in XZ plane, it can be any arbitrary rotation. Clear? Samajhan? So they form a, we call, okay, they under multiplication, okay. So because you know, if I take one rotation, follow it by the another rotation, that will give me the rotation again, is it? Let's say you rotate this by some amount, and this you rotate, let's say, by this amount, is it? So ultimately you are getting again the rotation, is it? Samajhan? So it is total a rotation. Clear? 2 rotations will give you the third rotation. Got it? So such kind of structures, okay, such kind of sets under a given operation form a kind of mathematical structure, what we call a group. Okay, so let me give you the definition of the group first. Okay, so let's say you are having some set G defined by some operation O. O is an operation. Okay, clear? So operation can be anything. It can be addition, it can be multiplication. You can devise your own operation whatsoever. Okay, so let's say you are having certain elements, let's say A, B, C, and so on, they belong to this G. Okay, so your G is this set. Okay, so now if these conditions are satisfied, let's say A operation B, okay, let's call if this is C and this belongs to G, is it? So that means if you, okay, let's say if this operation is addition, A plus B is another element, we call it C, and if this exists within this group, okay? So you make an operation between any pair, so you get another element, if that exists within the group, we call that as a closure relation, okay? So we call it as a closure. I can say this set is closed under this very operation. Clear? So now if another thing is the associativity, so you take any 3 elements within the group. So if this object, if this kind of is followed, so it is the associativity. Okay? And third is the existence of identity. Okay, so if the identity, let's call identity as this I, so you take an element A, multiply it, it is same thing A multiplied by E, so and sorry, I multiplied by A is same as what? A multiplied by I is equal to A. So and this I belongs to what? G. So that means this identity exists where? In G. Okay, and fourth is, so inverse. So let's say A inverse belongs to G. So this means inverse exists. Huh? Clear? So what is the inverse? A inverse A is equal to identity, that is same as A inverse. Clear? Got it? So this is, if this kind of structure satisfies these very actions, we call this G forms a group under the operation O. Okay? So now if you take any, let's say another thing, so that's an additional condition. Let's say if you take any 2 elements, if AB is equal to BA, okay, for all AB belongs to G. You take any pair, any arbitrary pair within the group, and if they are commutative, is it? I call this group as commutative. Okay, so it's an abelian group in that sense. So we call it as an abelian. Otherwise, okay, otherwise, what does that mean? AB is not equal to B. We call it as non-abelian. Okay, got it? Samajh aaya? So this is the definition of the group, and there are various terms. I will take rigorously it later on. I will start from these kind of examples to give you the flavor of the groups. Okay, these rotation groups. Clear? Okay, so now what we are having at hand. Okay, so we are having a set of matrices R, is it? And they satisfy. What is the condition they are satisfying? R transpose R, that is equal to identity. Is it? Okay, so before going to this thing, so these numbers, okay, this can be a discrete thing. Okay, so let me give an example, simple example. Let's take a set of these elements, 1 and minus 1. Okay, so let's define the operation here, multiplication. Clear? So you are having multiplication. This, let's check whether this is a group or not. Okay? So what is the first condition? Okay, so that is 1 into minus 1. Okay, so let's take 1 with itself. 1 into 1 is 1. 1 into minus 1 is equal to minus 1. Minus 1 into minus 1 is equal to 1. Rather, it is with itself. Okay, so it's 1. So all these three elements belong to what? I mean 1 and minus 1, that belongs to this. Is it? Okay, so that means it is what? Closure. Okay, so now let's take the second thing. 1. Okay, so it is because you are having only two elements, so SATUT is automatically followed. Clear? So SATUT is followed. So now let's take the inverse. So what is the inverse of 1? 1 by 1. Is it? Into 1 by 1. So what is that? So 1 into? So 1 is the inverse of itself. Is it? For every element there should exist inverse. So what is the inverse of 1? 1. Clear? So what is the inverse of minus 1? Minus 1. Okay, so you are having minus 1 into 1 divided by minus 1. Is it? Clear? So this is the inverse of itself. This is also the inverse of itself. Is it? So that means, so this is equal to, this should be equal to 1. Okay, so it should be actually equal to identity. If the inverse is there, A inverse A, it should be equal to identity. Is it? So this belongs to here. And identity is there. Okay, so identity also exists. So that means this set, this is a very small set, is it? It plays a huge role in physics. Okay, so we call this as a Z2 group, because it's having only two elements. Okay, so this forms a group, and it's an abelian group because elements commute with itself. 1 into minus 1 is same as minus 1 into 1. So this is an abelian group. Okay, so it's a discrete group because you are having a finite number of elements. You can count them. Clear? So now let's take the natural numbers under addition. Okay, so let's take the integers. Natural numbers do not form a group. So let's take the integers. Okay, so what is the set of integers? Dash dash dash, minus 2, minus 1, 0, 1, 2, dash dash dash. Clear? Okay, so what is operation here? Addition. Clear? So now let's check whether it is a group or not. Okay, so what is the first thing? So you take any elements, any two elements, sum them up. So this is the set of integers. So if you take, let's say, A plus B, so that's equal to C. That belongs to this set, set of integers. Clear? So you take any sum of any two elements. So you will get an element that will be there. Clear? So now let's take, important point is here, SATUT is followed because integers follow SATUT. Is it? What is SATUT here? So you take any two elements, let's say 1 plus 2 plus 3, let's say. So that is same as 1 plus 2 plus 3. So that is the operation. Huh? So this O means here plus. Huh? So it is satisfied. Huh? You take any three elements, any arbitrary three elements, check this, it is satisfied. Now let's take the third. So let's take the identity. What is the identity? Identity has to be under addition, is it? Not under multiplication. So 0 is the identity, okay? Additive identity we call it. 0 is also known as additive identity. So if you take any element a plus 0, that is same as 0 plus a, that's equal to a. So you get element back. Clear? So under addition, 0 gives you the concept of the identity, is it? So now let's take the fourth. What is the inverse? Huh? What is inverse?
Multiply with that number of identity.
You'll get the identity, is it? So for not multiply, addition. So you take 1 plus minus 1, is it? So that will give you 0. 2 plus minus 2. So negative numbers are the inverse under addition to the positive numbers, is it? Or positive numbers are inverse of the negatives under addition. Clear? So you take, it means like this thing, a plus minus a, what it gives you? 0. Clear? So it is under addition. Now what about the 0? What is the identity? 0 plus 0. 0 is the inverse of itself under addition. Clear? So because 0 plus 0 is what? 0. So under addition it is the inverse of itself. Clear? So that means this, okay, so you take any pair of elements, they commute, is it? So 0 into 1 is same as 1 into 0, okay? So it's an abelian group, huh? But this is a discrete group. Is it? Is this a discrete group? Okay, so this is a discrete group. Clear?
Sir, so we have seen two operations, this addition and multiplication. And there are two identities for the two operations. So if we are varying the, if we working in some another operation, which is right now unknown to us.
So you need to, okay, so if you are having an unknown operation, okay, so if you you can have a different kind of inverse, or you can have a different identity there. So it is not necessarily it will be same as 1 or 0. Clear? Okay. So you can define your own operation. Important point is in group. So you should be knowing the operation. What is an operation? Clear? You can define a kind of operation by yourself. Any arbitrary operation. Operation does not mean only the mathematical operation. Operation means any. You can take any day-to-day life example and see whether under this kind of, if I am doing this kind of arrangement, whether the structure forms the group structure or not. Yes.
So, sir, what are the criteria to define this identity for the particular operation?
So this is the criteria. Criteria is this thing. So if you are having certain operation, you assume some element, let's assume that forms an identity. When you multiply it with, okay, when you operate it on the any arbitrary element of the group, if it yields you that element back without changing it, that is the identity. Clear? So this defines the concept of the identity. Clear? So I should have put an operation here. Okay? It's like this thing. And this is the invertibility. Clear? Any question? Okay. So now let's take, so we will not interest, we will be doing only the continuous groups for the time being. Okay, later on maybe we will take the Z2 group. Okay, its utilization. Okay. So now let's take the set of R, is it? First tell me how many, there are infinite number of elements, is it? And each element is connected by each other, connected with each other, clear? Or in other words, you are having this structure as, okay, so let's first do it. Let's first do it, okay? First let's do it, then maybe you can understand it. Okay, so we are having this kind of set and I need to figure out whether this forms a group or not. So let's take the operation here, the multiplication of the matrices, because R is a matrix. Clear? So our operation here is what? Multiplication. A matrix multiplication. Yeah? It's not simple multiplication, matrix multiplication. That means if you take any two elements from this very group, okay, so they satisfy the matrix multiplication. Clear? So they are square matrices. Okay, so these are the square matrices of, for the time being we will take them 3 by 3. Clear? Or any arbitrary, you can be having this n by n, there is no problem. What I need to do, I need to figure out the closure relation. Clear? Got it? Okay, so how to do it? The first point is how I can figure out the closure, is it? So I will take two elements. Okay, so let's consider two rotations, R1 and R2. Is it? Okay. So when this should give me the closure. So if I take their rotation, let's say R1 multiplied by R2, so that rotation should satisfy me this condition. Clear? So that should be also an orthogonal, because I need this kind of condition. Clear? So individually I am having R1 transpose R1, that is equal to identity. R2 transpose R2, that's equal to identity. Clear? So Shaman? Okay. So they belong to, let's write this as let's write this as G. Huh? Okay. So let's take now R1, R2. So these are two rotations together. Clear? So let's check the transpose of this thing. Like this thing. So this is a collective rotation. Huh? Clear? So this I can write R2 transpose R1 transpose. Okay? R1, R2. Because when you take the transpose, it will reverse the objects. Clear? Okay. So how much is that? So it is R2 transpose. So this is equal to identity. This R2. So what is that equal to? Identity. So what it means? So it means this is R1, R2 is an element of this G. Clear? Got it? Because it satisfies this very condition. So it means this is closed. Clear? Closure is satisfied. So the assignment for you people is to show the associativity. Okay? So show what? Associativity. Clear? So you need to check the associativity property of what? This very group. So how many elements you will consider? 3 elements. So you will consider R1, R2 and R3. So okay, so you will consider first R2, R3, okay, then multiplied with R1, is it? So much, so clear? So it should be like this thing. So this should be same as what? R1, R2, R2. Clear? You need to show it. So it's not a proof. Associativity means this thing. So what you need to show this? This kind of product should give you identity. So left hand side and right hand side should give you the identity. Clear? Got it?
Yes.
Okay, so you should understand it, what it means. Third is the identity. Anybody? Can you tell me what is the identity here?
R1 inverse R2.
Identity, yes. What is the identity here? So you are having a matrix multiplication, is it? So under matrix multiplication, what is the identity? Identity matrix. Now we need to understand physically what identity matrix means. So I can take I, okay? So multiplied by R, that is same as what? R times I, that is R, okay? Clear? So it clearly satisfies this very condition, is it? R transpose R is equal to identity, is it? Is that true? Is that true? Does, okay, so the first thing is I transpose I, that is same as I transpose, is it? That is equal to identity. So that means this I belongs to this very set. Now what identity means in a rotation? Huh? Yes, no rotation at all. Identity means you start from there. Your baseline is what? Identity. That means no rotation. To identity you add small rotations. Clear? Got it? Okay. So now let's take the fourth element. What is the inverse? Okay, so from this very condition, you are having R transpose R is equal to identity. It means what? R transpose is same as R inverse. Clear? So that means inverse of this R exists. Got it? What is the inverse? What is the inverse of R? That's R transpose. Clear? Okay. So you need to actually check whether this inverse satisfies this condition or not. Okay? So what is the definition of the inverse? How we define it? So you multiply inverse. Okay, let's take the inverse. So R inverse multiplied with R, it should give me identity. Is it? So you need to check this R inverse. Okay, R inverse R transpose R inverse. Sorry, R inverse. Is it? So what that is? R transpose R inverse transpose. So am I doing correct?
Yes, sir, yes, sir.
Huh? Yes, it is correct.
Correct.
Okay, so this is equal to.
Yes, sir.
So what this is?
R transpose.
Huh?
It is same.
It is one identity.
Yes, sir.
Huh? Is it? So it satisfies. Is it identity? What is R inverse R?
That's the first.
That is what identity. Is it?
It's a middle two.
Huh?
Identity, and then first and the last is identity.
Okay. What is R inverse?
Transpose and R.
That is R. Yes. Good. So you are having R transpose here. What is R inverse transpose? If I take the transpose, it is not T here. If I take its transpose, it will be simply R. Is it? So then you are having R inverse.
No, sir.
Okay, so this R inverse will be R transpose R. Clear? What is by definition R transpose R? It is identity multiplied by. So it is I. Clear? So we have to use this very definition, is it? Got it? So that means that this R inverse satisfies me the condition, is it? Got it? It means R inverse exists. Clear? Okay. So now we are, okay, in general, rotations do not commute with each other. So you are having the fifth condition, R1, R2 is not same as R21. So that means it's a non-abelian group. Clear? Okay? So we call this rotation group as a continuous group. Okay? So the continuous group is that you can change. Okay, so the continuous groups you can think this way. So they are defined by certain parameter. Here the parameter is angle, is it? You can change that parameter continuously within the given interval. Clear? And you are having here theta as the parameter of the rotation, let's say. So you can change it from 0 to 2 pi continuously. Clear? Got it? So this we call as, okay, continuous group. And how many elements are there? There are infinite number of elements. Clear? So now let's write the examples of this rotation. Any question till now? Okay. So you can see, let's take the rotation about, okay. So rotation, let's say, first let's take in XY plane. So usually you call it about Z axis. Clear? How is that? So let's write theta as the parameter. Let's write that RZ of theta. So what is that equal to? Cosine of theta, sine of theta 0, minus sine of theta, cosine of theta 0, 0, 0, 1. So this is the rotation matrix, is it? And theta goes from 0 to 2 pi. Clear? And you can have the another rotation, YZ plane. So what is that about? X-axis. Clear? So that means you need to keep this is x-axis. Clear?
Yes, sir.
You need to keep this x-axis as identity. Clear? So this is z-axis. Clear? So let's write that as Rx to an angle psi, let's write phi. Okay, so that's equal to identity 0, 0, 0. So it will be what here? Cosine of phi, sine of phi. Okay, 0 minus sine of phi, cosine of phi. Clear? So now if I am having rotation, okay, so these are the possible rotations. Clear? Okay. So what that is? XZ plane are about y-axis. So let's write that as Ry and some psi as the angle, because you are having three different angles here. Okay. So you can. So I have defined it through the planes, is it? So I mean simple xy plane, yz plane. These three types of planes you can define through the Euler angles as well. We can naively say theta, phi, and psi, they form the Euler angles. Clear? Okay. Okay. So what is that equal to? So no. So it is zx. Clear? So it will be
cos psi.
Just tell me.
Cos.
No. Just tell me. It is z, is it? And zx plane. Just tell me. So yes, it will be cos of psi 0, sine of psi 0, 1, 0, minus sine of psi 0, cos of psi. Clear? Got it? Okay. So now you can see Rx, Ry, they do not commute with each other, is it? Okay? Okay, so now look here. These rotations depend on these parameters, is it? And we can change them continuously. Okay, so let me define it. Okay, so let's take a concept. We define the generator of the rotation. Yes?
ये clear नहीं आ रहा है. ये समझने कैसे लिखे आपने?
So what you need to take? What is here involved? X and
Z.
So that means for x you do cos, for z you do sine. Clear? So this is x, y, z. Is it? Clear? So look here. So this is what? Y, z. You give y to cos and z to sine. Clear? And keep this as identity. What is fixed here? X is y, is it? Let's fix it. It's row and column. Row and column you keep as such. Okay, so here z is fixed, it's row and column fixed. Clear? Don't do with that very column and row. Okay? So rest you fill up with the number, these functions. Clear? So let's define a concept of what we call it the generator of the rotation. Clear? Okay. So let's take me first to the z-axis. Okay, so we define it. Let me define Jz, okay, as 1 by I, like this thing. Okay, partial by partial. What is the parameter? Theta in that case. Okay, so acting on this Rz theta, and you take then theta equal to 0. Got it? So this is how I do. So what I mean by that, I say this Jz generates me the rotation about z-axis. Clear? Got it? You got my point. So I'm just giving you some quick definitions, but you will see it in general. Okay, so how we put everything in terms of the generators. Then you will see why this theta is equal to 0 here. Clear? So what I mean by it. Okay, so let me, what you know already. So let me take from there. So if you remember, you are having the rotations, you write like this. I, j dot theta, is it? So let me write jz theta. You know it? So, huh?
Yes, sir.
So this is the rotation about what? Z-axis. It gives me the rotation matrix Rz theta. Clear? So we'll see in a moment it is the same thing. Clear? Got it? So what I call Jz? Theta is a parameter and Jz is a generator corresponding to parameter theta, is it? Jz generates rotation in xy plane or about z-axis. Clear? Got my point?
Yes,
so how I will figure out this Jz? Okay, if I have the information of Rz, and let's assume I don't have the information of Jz. Clear? So let's say I know this thing and I don't know this thing. So So how I will obtain this jz? Just differentiate this exponential with respect to theta, is it? So let's differentiate it. So that means partial rz by partial theta. So you differentiate it, it is minus I jz, is it? So what do you get? Minus I jz theta. So in other words, if I take theta equal to 0, so what it is? Theta equal to 0. So it is minus I jz. What is your jz then? So I should introduce that minus. So it is I partial rz by partial theta, theta equal to 0. Clear? Got it? So this you know, but I started from here. Okay? So it's it's plus here, I think. So is this a plus sign here? So we'll see. We'll see. Oh, so this is actually the way how we define the generator. Clear? Okay, so if you know the point is here, if I know the generator, I can know the rotation matrix. If I know the rotation matrix, I can know generator. Clear? Got it? Everything we do in terms of the generators. Okay? So you will see actually when we'll be doing it in full blown, why the actually you should have got an idea from quantum mechanics as well. Okay? So you had an angular momentum algebra, is it? Clear? Okay, so forget if you don't know. So how much time is remaining?